Today I'll be talking about locally decodable codes in resource-bounded channels. My name is Shubhang, and this is joint work with my co-authors Jeremiah Blocki and Samson Zhou. Our story begins with the need for reliable communication. As the next step in space exploration, humanity has started sending its first astronauts to Mars. Everything goes smoothly, and lo and behold, our astronaut friends have reached Mars. They must now relay news of this amazing feat back to mission control on Earth. They decide to send the name of the planet to convey their message. However, space is a noisy medium, and their transmission gets corrupted along the way. Knowing that space is noisy, what our astronaut friends should have done is added some redundancy to the message so that even amidst corruptions, the people back on Earth would have had enough information to recover the original intended message. In this example, simply repeating the message thrice allows recovery of the original message by a majority vote on the repetitions. Well, now that the astronauts have reached Mars, Earth wants them to confirm the age-old question of whether there is flowing water on the planet. Once again, in order to relay their exciting observations, the astronauts use the previous repetition strategy. Space corrupts the transmission, but Earth is able to recover the original message. Take a look at the message. Is decoding the entire message really necessary? It looks like simply decoding the first symbol conveys all the necessary information. So Mission Control decides to cut to the chase and get just that symbol. They can do that by making 3 local queries to the transmitted message and recover the intended Y symbol by a majority vote. So let's focus on that second scenario and abstract away the details of what just happened. In our setting, a sender and receiver are communicating over a noisy channel. We saw that it was a good idea for the communicating parties to encode and decode the message for reliable message recovery. In particular, the receiver is interested in recovering only the ith symbol of the original message. To potentially avoid spending computational resources in reading the entire transmission, the decoder is given oracle access to the corrupted transmission or the code word. The encoder maps messages to code words, and the decoder can ask the oracle for specific symbols of the corrupted code word. It must output some target bit of the original message. The inputs may be random or adversarial depending on application. We should also look at the channel. It can also be modeled as random or adversarial depending on application. Note that finding the right channel model is a challenge, one that will be the motivation behind this work. In our communication setting, the channel substitutes a row fraction of the symbols of the code word and outputs the resulting corrupted code word to the decoder. Here's an illustration of how the previous scenario is captured by our model. Note that due to the high error rate of a fourth, this is not locally decodable under our repetition code scheme. 2 of the Y's have been corrupted, and one would need 7 repetitions for 3 symbol substitutions in general. So what are the goals of our model? Well, we want the decoding to be correct with good probability. We also want to minimize the code word length during encoding, as well as the number of queries to the corrupted code word during decoding. Note that the number of queries to the code word is called the locality of the code. And so, high locality means a high number of queries, which is undesirable. Finally, we want to maximize the number of errors that our code can tolerate. Taking a step back, all these are saying is that we want correct decoding while minimizing communication cost and maximizing communication robustness. Modeling the noisy channel is crucial to the design of codes. Historically, there have been two major channel models that people have considered: Shannon channels and Hamming channels. On the one hand, Shannon channels flip each bit of the code word independently and identically at random with some known fixed probability. On the other hand, Hamming channels introduce worst-case error patterns into the code word subject to the error rate. Both of these have their pros and cons. The main pro of using the Shannon channel model is that one can construct very efficient locally decodable codes with desirable properties. However, the error patterns introduced by these type of channels don't capture nature well. For example, burst errors, where lots of errors happen directly one after the other, aren't well captured by this model. Due to the worst-case nature of Hamming channels, constructions and bounds against these channels are applicable for any setting. Unfortunately, there aren't good locally decodable code constructions known that have good parameter trade-offs. Here are some locality versus code word length trade-offs from current literature.
Hadamard codes can be locally decoded with just 2 queries, but the length of the code word is exponential. There are no known constant rate constructions that achieve polylog locality.
It seems that Shannon channels and Hamming channels are extreme models where the former assumes knowledge of all channel properties, whereas the latter assumes no knowledge of channel properties besides it being worst case. This begs the question of whether there is something practical in between these two extremes. And the answer to that question is yes. Recent lines of work have started focusing on computationally bounded Hamming channels, which introduce worst-case error patterns into the code word, subject to some computational restrictions on the code. Two examples of such channels are PPT channels, introduced by Lipton, and simple circuit channels, introduced by Goswami and Smith. These also have their trade-offs. PPT channels have amazing LDCs with excellent parameter trade-offs. However, the current constructions require private key exchange between sender and receiver prior to communication. Simple circuit channels admit good codes as well. However, existing constructions are not local. So our work begins by asking the question, do there exist computationally bounded Hamming channels with good locally decodable codes? Let's go back to our Mars mission. When astronauts are communicating with Earth, what they are doing is beaming back the message using electromagnetic waves. Now, the maximum Earth-Mars distance, as well as the speed of light, are bounded. They're large, but bounded nonetheless. We can conclude that any adversary, which in our case is space, has bounded amount of time to corrupt the transmission before it reaches Earth. Here, the maximum time, if you plug in our observations, works out to a little over 22 minutes. The point is that any adversary is not computationally unbounded. So, can including this time bound help in code constructions?
We can ask the same question using any general computational resource. Towards this, let's define resource-bounded channels as introducing worst-case error patterns into the code word subject to the resource bounds. Any channel encountered in nature will be resource-bounded, or at least sequentially time-bounded, as an adversary has to introduce all corruptions into the code word before the code word is handed to the receiver. Given the discussion so far, natural questions that arise are whether there exist good LDCs against these channels. Is there a need for trusted setup? And we can even go further to ask the more general question of what are simple characterizations of LDC-friendly channels. We answer all three questions in an idealized setting called the random oracle model, where a cryptographic hash function, such as SHA-3, is modeled as a truly random black box function.
In particular, we will introduce safe functions as a general characterization of LDC-friendly channels. We show constructions of such functions in the parallel random oracle model for various resource-bounded channels. We give a general framework in the PROM for designing LDCs against channels admitting safe functions. We can instantiate this framework for resource-bounded channels using the above-mentioned safe function constructions. The framework requires no setup and achieves binary LDCs with excellent parameter trade-offs. Jumping slightly ahead, the security of our framework information theoretically reduces to the security of one of its constituent technical ingredients. It turns out that a standard hybrid argument fails to argue this security. To tackle this, we introduce a general argument strategy that may be of independent interest and could be useful for coding theoretic problems against bounded channel models. The first technical tool needed will be private LDCs. These are LDCs defined in the setting where the sender and receiver possess a shared key that is secret from the adversarial channel. The communicating parties may then use the randomness from this secret shared key in their encoding and decoding procedures. Private LDCs were defined by Ostrovsky, Pandey, and Sahai in 2007. In that work, they also demonstrate explicit constructions of such codes with various desirable properties. I would like to briefly highlight that these codes achieve polylog locality with high probability of correct decoding. The main goal of our final framework will be to achieve similar parameter trade-offs for resource-bounded channels without any setup assumptions. The second and final technical ingredient which we will need is the notion of a safe function. Intuitively, a function is safe against a channel if the channel cannot predict the value of the function given the input. In slightly more formal terms, F is delta safe against a class of algorithms if no algorithm in the class can predict the value of the function with probability greater than delta. Let's look at two intuitive examples of safe functions in the random oracle model with random oracle H. For our first example, consider a sequentially time-bounded channel with time-bound t. It is trivial for this channel to compute h to the t. However, h to the t plus 1 is computable with at most negligible probability, and so is safe for this channel. For our second example, Alvin et al. Showed that the function scrypt is maximally memory hard. Thus, scrypt cannot be computed by space-time bounded channels and is safe for these channels. Note that these are just intuitive definitions and examples. We give formalizations of various resources and discuss safe function constructions for these resources in our main paper. The main idea will be to use the channel safe function to extract a secure key that can be used in encoding and decoding. So how do we extract the secure key? Let's consider a random oracle H, channel C, and delta safe function S. Superscripts represent oracle access, and subscript represent function parameters. Given this setup, we can define an extract function in the PROM as follows. Here, the circle represents string concatenation. The idea is that it is hard for the channel to compute the safe function, and so hashing the output of the safe function appears effectively random to the channel. Hashing indexed evaluation of the safe function and concatenating them together allows for controlling the length of the generated key. So conditioned on the event, where the channel never queries the random oracle, with the string having the evaluated safe function as its suffix, our extracted key appears random to the channel. If the encoder can send a short seed to the decoder, both the encoder and decoder can use the extract function to generate a shared key. Since the channel cannot compute the key, it is effectively a private shared key. This key can now be used to bootstrap private LDC constructions. Let's put everything together to form our final framework. The sender has a message that it wants to send to the receiver. To do this, the sender first samples a random seed of short length and uses the extract function to compute a key that is secret from the channel. Next, the encoder uses an existing private LDC encoder to encode the message, which is now ready for transmission. However, the decoder should also know the random seed so that it can also extract the appropriate secret key. So, the encoder encodes the seed using first a repetition code, and then encodes each repetition using a constant rate error correcting code. Finally, the seed encoding is appended to the message encoding and sent over the channel to the receiver. Being a local decoder, it gets query access to a corrupted version of the appended encodings along with an input target index which it wants to decode. To generate the secret key, the decoder first randomly samples some possibly corrupted seed encodings and decodes them using the decoder of the constant rate code. It then takes a majority vote over the decoded seeds to get back the original seed. This seed is used to extract the secret key using the extract function. Finally, the extracted key is used in conjunction with the private LDC decoder to decode the required index from the message encoding. This concludes our encoding-decoding framework. Let's make the ideas from the picture of the previous slide more concrete. Note that all parties have access to the random oracle in our model. Our 5-step encoder does the following. It first randomly samples a seed and extracts a secret key from the seed using the extract function. The encoder then computes the private LDC encoding of the message using the computed key. Finally, the encoder encodes the seed using a constant rate code concatenated with a repetition code and outputs the concatenation of the two encodings as the final code word. On receiving query access to the corrupted code word, our 3-step decoder does the following. It first decodes the seed, extracts the secret key using the extract function, and finally decodes the target message bit using the private LDC decoder with the extracted key. Note that sampling the random seed and encoding it can be pre-computed, and the seed length is chosen sufficiently small to maintain locality, but large enough to ensure security of the entire framework. Let's quickly discuss an instantiation of our LDC framework. Here's the instantiated framework from the previous slide for reference. Recall that Ostrovsky, Pandey, and Sahai gave explicit private LDCs with various desirable properties. We use these private LDCs in our instantiation. Furthermore, we can instantiate the constant rate code in our seed encoding with the justice encode. Our framework now works with these constituent codes and achieves the properties exhibited by private LDCs with just a small loss. I would like to emphasize that this is in the absence of any private key setup. In conclusion, resource-bounded channels better capture realistic error patterns that occur in nature. We can construct efficient LDCs for resource-bounded channels, and we can do so by using safe functions. These can be used to extract private shared keys between the communicating parties. This allows for the bootstrap off of private LDC construction using the extracted keys. In our main paper, we discuss how to construct safe functions for various types of resource-bounded channels. We also discuss candidate safe function constructions without random oracles, example, by using time lock puzzles. Our work paves way to a few interesting open questions. What are other applications of safe functions? And are there LDCs for resource-bounded channels without random oracles? In this extra section, let's look at an argument that shows our framework is secure. The main idea is to reduce the security of our framework to that of its constituent private LDC. The way we argue this at a high level is as follows. First, assume that some resource-bounded channel can corrupt code words beyond recovery with significant probability. Then consider this channel in the private key setting. We can show that in this setting, the channel can corrupt code words beyond recovery with significant probability, which contradicts the security of its constituent private LDC. So how do we argue this? Can standard techniques suffice? Let us try to use a standard hybrid argument which follows the argument template from our previous slide. We define the following experiment using two hybrid encoders. Encoder 1 is our framework encoder. Given a message, it samples a seed, extracts a key, and encodes the message using a private LDC encoding using the computed key. The output of this encoder is the concatenation of the message encoding along with the encoding of the seed. On the other hand, encoder 2 follows the same procedure for encoding the input message, but appends the encoding of some random unrelated seed. The goal of the experiment is to distinguish between these encodings. We would like to argue that these hybrid encodings are in fact indistinguishable, and that resource-bounded channels cannot fool the distinguishers. There are some issues with this argument. If the distinguisher could evaluate the safe function, then these encodings are trivially distinguishable, as one of the seeds is unrelated to the encoding. However, if we assume that the distinguisher cannot evaluate the safe function, then this distinguisher does not model the decoder, and therefore this argument does not prove security of our framework. To overcome this, we introduce a new hybrid argument. Our experiment has two phases. The hybrid encoders remain the same as those in our previous attempt. In phase 1, one of the encodings is selected at random and given to the channel. The channel corrupts the encoding and outputs the corrupted code word to conclude the phase. In phase 2, the distinguisher is given the secret key, the original message, and the corrupted code word, but it does not have access to the random oracle. With this setup, the distinguisher tries to predict which hybrid was chosen. In our main paper, we showed that any attacker-distinguisher pair succeeds at this prediction with at most negligible probability. The final argument proceeds as follows. Assume that some resource-bounded channel can corrupt a code word beyond recovery. Then, this channel can be used as the attacker in phase 1, and a distinguisher can simulate the private LDC decoder with the appropriate key in phase 2. This allows hybrids to be distinguished with non-negligible probability, which gives us the required contradiction. A few observations are that the distinguisher is computationally unbounded.
And that's why the private LDC decoder can be simulated exponentially many times in phase 2.